There are two broad classes of molecular forces to consider, intra and inter. We've already learned about intramolecular forces, or bonds, and in this video we'll be learning about intermolecular forces that happen between separate molecules. And there are three main classes of intermolecular force, and they're all some variant on an electrostatic attraction. The first type of intermolecular force we'll talk about are dispersion forces. So consider an atom like beryllium. So beryllium has 4 electrons, and those electrons are in spherical orbitals. Beryllium is electrically neutral, and its electron density is spherically distributed around the nucleus. This is a simplified diagram of what's happening there, where I've combined the two orbitals together, but it represents what's happening on average. You have a positively charged nucleus in the center, and a roughly even distribution of electrons around that nucleus. You have an electrically neutral system. In reality, though, the electrons are moving around constantly. They're not sitting motionless in space. And that means sometimes they're going to be distributed unevenly. If they're distributed unevenly, one side of that atom is going to be slightly positive and one side is going to be slightly negative. You have the formation of what's known as an instantaneous dipole. Dipole being two poles, one positive, one negative. And instantaneous because it happens as the electrons are moving around. What happens is the positive side of that instantaneous dipole that forms spontaneously is going to attract the electrons in one of the nearby atoms. And that's going to cause the two atoms to be briefly attracted to one another. And this can also happen with larger systems like entire molecules. And this type of dispersion force is really only significant when the molecules or atoms are very, very close together. Larger molecules tend to experience larger dispersion forces because it's easier to form instantaneous dipoles in a larger system. And we can roughly correlate that to increasing molecular weight corresponds with increasing dispersion forces. And dispersion forces are also going to be impacted by molecular shape. So the shape of a molecule is going to control how close it can get to another molecule. So we're going to consider, as an example, two different molecules with the same formula. We're going to look at the linear version of C5H12. And I'll draw this molecule without any hydrogens on it for now, just because hydrogens are very, very small, and this will help with clarity. If we bring another C5H12 molecule close to this one, they can get pretty close together. The molecules almost stack together. They can get very close. They have a large dispersion force. Then we'll look at another version of C5H12. If we bring two of these molecules together, it's hard to get them as close as the linear version. This more three-dimensional structure is harder to bring close together, and it's going to result in a lower dispersion force. Another type of intermolecular force is the dipole-dipole interactions. And this works very similar to the dispersion forces, where an instantaneous dipole forms and attracts the opposite charges, and the positive side of that dipole attracts negative charged electrons. The difference is that dipole-dipole forces are related to permanent dipoles. And because permanent dipoles are required, this means you need polar molecules, or molecules that have electronegative elements in them. So consider this example. The nitrogen is the most electronegative element, so this is a polar molecule, and you have a permanent dipole. If you bring another one of these molecules close together, the positive and negative ends can line up. And the strength of these interactions is going to be directly related to the polarity of the molecules. More highly polarized molecules are going to have stronger interactions. And collectively, the dispersion forces and dipole-dipole interactions are known as the van der Waals forces. Hydrogen bonding is a special subtype of dipole-dipole interactions that is typically much stronger than any of the other van der Waals interactions. And these interactions happen when you have a hydrogen bonded to a very electronegative atom, usually fluorine, oxygen, or nitrogen. When hydrogen is bonded to a very electronegative atom, you end up with a very polar bond. This means that your hydrogen is very positive and the electronegative element is fairly negative. So the hydrogen, the very small positive hydrogen, is going to form a dipole-dipole interaction with a nearby electronegative or negatively charged atom. And the reason that these types of dipole-dipole interactions, these hydrogen bonds, are so much stronger is because of two reasons. One, the bond is very polar. And two, hydrogen is tiny. It's effectively a bare proton now because so much of its electron density has been pulled away by the polar bond. And that means that the hydrogen can get very, very close to the other molecule. Remember that any electrostatic attraction is going to depend on how close things are and the magnitude of the charges. You have a very positive hydrogen and you have a very small distance. The relative strengths of intermolecular forces have ion to dipole interactions being the strongest, hydrogen bonding being the next strongest, then dispersion forces, and then dipole-dipole interactions. If you have two different molecules of similar masses, the strength of the interaction between these two different molecules is going to be determined by dipole-dipole interactions, hydrogen bonds, and ion-dipole bonds. If you have wildly different masses, then dispersion forces are generally going to be the one that determine the strength of the intermolecular interaction.